Hello, everyone. I believe we can start with the fifth lecture of our information visualization series. Today, we are going to be talking about multivariate data. So the question that we're going to aim to answer is how do we handle n-dimensional data in a two-dimensional space when n is greater than 2. We are going to have an overview of dimensionality reduction techniques and also visualization techniques, how to tackle multivariate data just using visualization. So there's going to be some math in today's lecture, but it's there to illustrate the point. So I'm not going to expect you to know all the various equations that will appear on these slides. It's very important that you understand the techniques on an intuitive level, and you'll be able to use them. So if we're talking about multidimensional data, so two-dimensional data is obviously not a problem. We have a two-dimensional screen, so you can take any of the plots we have mentioned. You can or you can take more. You can inspire yourself on this DataVis catalog. It's here as a nice extra resource for you. But of course, you know, maybe not all the charts there are that useful. So I leave it as an exercise to the reader to apply all these various laws of perception and good visualization that we have learned in the previous lecture to select the right one. But nevertheless, the DataVis catalog might be able to expand your minds somewhat. Regarding 3D, as will also be no surprise, is also quite doable. You can, for instance, use a 3D scatter plot. This is again our favorite iris data set of 3 classes of iris flowers. And of course, this plot is only useful if you can rotate interactively. So you know, this projection, this is a static plot, it does convey a couple of clusters, but it would be but you know, the static projection from 3D to 2D doesn't work that well. If we would have a rotate button here, it would be way better and considered good visualization as a single plot. We have also been over encoding multiple dimensions into different visual artifacts or visual dimensions within your visualization. So if we recall the laws of pre-attentive display, that if we combine position of the glyph with simple glyph properties, then we have a functional pre-attentive compound. So we have a plot or a set of glyphs that stand out on dimensions that we want them to stand out pre-attentively, so naturally to our eyes. And if you recall the laws of pre-attentive display in detail, you might remember that we either want to encode a simple dimension, so the glyphs stand out on a simple dimension such as shape or color, or max 2 so-called separable dimensions, which can be, for example, shape plus color, as we see on this plot. Those would be those where you can select where you will visually split your point of view, basically. So this is a plot that we have mentioned as a good example in lecture 2, I believe. And we see that here we easily encode 4 dimensions. On the x-axis, we have the population growth rate. On the y-axis, we have the GDP. Then we have the, let's say, urbanness or low/high urban dimension, which is the glyph shape. And literacy is encoded by color. Also nicely contrasting color. So if you remember lecture 3, we talked about how contrast could be important. So here this entire thing is made easier because these 2 colors are very, very contrasting. I think near opposite, because we have dark red and dark cyan, which is opposite on the color wheel. You can try it out if you look at the wheel again. So in a sense, this is a 4D plot. You know, even though it's in 2D and we haven't done any projections. We have also seen a 5D plot already. So this has been mentioned a number of times as well. Here we can encode income on the x-axis, life expectancy on the y-axis. Continent is the glyph color. The bubble size is the size of the population at the time. And the fifth dimension is the time. We have an animation. So that's the fifth dimension, and we even add sixth dimension by a tooltip. So here I have clicked on a random glyph, and we see that this is France 1822. So this encodes the particular country. So that's a sixth dimension actually. So interaction can also add dimensions functionally to our visualization. So this is what I have just said. It is there for posterity if you use these slides as study material. But we've been over this. So interaction is a quite useful tool. That's the emphasis of this slide. So what about encoding 5+ dimensions? Well, it's quite difficult. So there is not an easy method to do this, and the problem is that our human imagination basically doesn't work very well with high dimensional data. So we can easily visualize up to 3D, some of us at least, and beyond that, like visualizing 4D, 5D, 6D space is already a bit difficult. So, and even if you don't talk strictly about 5+, if we talk about the 5D or 6D interactive, as we have seen before, it's not very easy every time, because if you look at Rosling's plot, the one on the previous slide, the bubble chart, the population bubble chart, it's kind of a masterclass in visual variable encoding. I mean, the guy got a TED talk for it, so it's pretty good, right? He has chosen the right intuitive type of encoding for each variable, which is not always possible. And it also involves animation. One of the dimensions is animation, which we have talked about might be problematic, right? So it's a very niche encoding that is not right for all types of data. So even the 5 to 6D is quite difficult already. And encoding more and more dimensions visually, basically, it will make the plot unreadable. Or at best very unintuitive, and you would really have to go over each individual glyph, decode each individual glyph, so that completely destroys your ability to visualize larger data. So multivariate methods, what are they? So a survey by Liu, which is quite a nice survey in the InfoVis community, uses rather useful categorization. So first, you can have data transformation, which is analysis-centric methods such as dimension reduction, regression, subspace clustering, feature extraction, data sampling, or abstraction. So these are recomputations of the data. Then we have visual mappings. So those are visualization designed and equipped to handle multivariate data. And then we have so-called view transformations. We are not going to go over these in this lecture, but those are screen space rendering manipulation techniques. This is the key figure in the survey. So here is a nice summary of what we can do, and we're going to go over a couple of those subdivisions, and starting with dimension reduction. But if you're interested in things that go beyond what we talk in the lecture, then you can always so the ref for this is in the optional reading, and you can quickly refer to the individual methods if you're interested. But we're going to go over the most important ones that are used in the state of the art. So dimension reduction. So we're talking about data transformations. So before we start on that, we have to talk about statistical techniques and summaries, right? So we can do a lot of things statistically with the data, especially with numeric data. We have machine learning available, which to some observers might seem like applied stats as well. So it's a related discipline. And both have been proven to be quite effective and reliable, right? And they are. So what's the problem? So why don't we just summarize the data set, just use machine learning and be done with it, right? Why do we need to visualize it? Well, consider a problem of so-called Anscombe's quartet. That's a quartet of that's 4 bivariate data sets. So they only have XY coordinates. So a very simple data set, not a problem for visualization, right? And each of those data sets has 11 data points. Mean of X is equal to 9 exactly. Mean of Y is equal to 7.5 to 2 decimal places accuracy. sample variance of X is 11. Sample variance of Y is 4.125 with a deviation of 3 thousandths. The correlation between X and Y is 0.816 to 3 decimal places for all 4 data sets. And they even have this pretty much the same-ish linear regression line, which is given by the formula below. So 0.5x plus or Y equals 0.5x plus 3. So so the trend is kind of similar to, and it's accurate to 3 and 2 decimal places respectively. So from this, we see that the summary of these data sets is remarkably similar or the same pretty much, and we only have 11 data points. So those data sets must be very similar, right? And they're not so much. So if you actually visualize them, then you see that they're considerably different. So Anscombe's quartet is a technique. Those data sets are of course artificial. They have been created by the guy called Anscombe. I think Greg Anscombe was his name, to demonstrate that over-reliance on statistical summaries is not the right thing to do all the time. And this is a very simple data set of 2 variables, bivariate data. So if we have more dimensions, then we will have many more tricky artifacts than we can have in 2D. So note that statistical summary and trend techniques are very useful, no doubt about that, but they are not the golden ticket if you want to convey information about the data. This, I believe, is part of the niche of visualization. So visualization should offset the weaknesses of summarization, right? And that's why it is very useful to data scientists, even as an internal and debugging tool. So even if you're not, so I'm a data scientist myself, and I like to visualize intermediate results of my analysis all the time because even before I start making presentations for the end audience, basically. So it could be maybe to those of you interested in data science, you might want to incorporate visualizations if you haven't already. It's actually quite useful. And we have also noted that the underlying data distribution is important, its structure, and it's not always captured by the summaries, starting with already simple things like the Anscombe's quartet. So we have to bear this in mind. So we cannot just summarize the data set. That's an extra motivation for dimensionality reduction. And now that we're doing dimensionality reduction, so an important piece of intuition that we need to keep in mind are the manifolds. So in a very intuitive terms, consider manifolds as the native dimensionality of your data. So the dimensionality in which, if you plot the data, you are able to capture it very precisely, and you're not losing any information by plotting it in the manifold dimension. The key intuition here, why this is useful, is that the manifold dimensionality, or the native dimensionality of your data, is for real data, it's almost always lower than the data dimensionality. So that means that you can visualize the data in m dimensions without loss of information, which is exactly what we are shooting for with visualization. The manifold theory is very heavily utilized in machine learning or artificial intelligence, but also in InfoVis. And it's best shown on an example, right? So what are the manifolds? So here we have on the right, you see the Swiss roll data set. It's an artificial benchmark data set, which has been used to judge the efficiency of dimensionality reduction methods, mostly. But I believe that it demonstrates the concept very nicely. So this is 3-dimensional data. You see that the roll is 3D, but M, the manifold dimensionality, is actually 2, because you can unroll the roll into a rectangle. So this rectangle captures exactly the same data as this roll. So if you're trying to learn the manifold, or you're trying to reduce dimensionality to the manifold, you're going from 3 to 2, and ideally your method would do this exactly. It's very difficult to do, and not many will do this, or none of them will do this, I believe. But the more similar to this, the better your method is, basically. So this is the intuition behind the manifolds, which is a term we might be using further. So either manifold or reduced dimensionality space. That's it's a synonym. And now we're talking. We're in the InfoVis course. So what does that mean for us?
There's a question from Martin.
Okay.
On the Swiss roll example, isn't the distribution of the data lost in the resulting visualization?
So if the point here, which is important, is that the important part of the data is what's encoded by these colors here. That's a very good question. So the role, the turn is basically just like an artificial thing. So it's an artificial data set. So what matters, what's the data distribution, is those colors. So what you want to keep is you want to have a rectangle, and you want the rainbow. That's your distribution that you're trying to preserve. And this is basically the role is making it more difficult. But it's a very good question. I failed to talk about that. Thank you. Okay.
Yeah, all clear.
Okay, perfect. So in InfoVis, n equals 2 by force, because we only have 2 dimensions to plot our data in. It's as simple as that. And basically, all dimensionality reduction methods for InfoVis try to find such manifold, to that 2-dimensional manifold, which is, of course, it might not be native, right? Because if the true m is higher than 2, we are going to lose information. There's no way around that. If your data or the properties of data that you want to capture have higher dimensionality than 2, then you are going to lose information. So and that's very often the case. Very few of the real data sets are really two-dimensional, basically. So so that's a catch. And I mean, setting m equals 2 by force is actually quite brutal. So in machine learning, you don't need m equals 2, because you're doing analysis that is not visual. So if you reduce a 1,000-dimensional data set to 100 dimensions, then you have done a massively good job in machine learning. But for InfoVis, it won't do. So this is actually quite brutal. And but if the dimensionality reduction algorithm preserves the distribution, so the useful information that we're trying to keep, such as the rainbow pattern on the Swiss roll data set, then we're still fine, basically. So it's a bit wonky. We don't have exact preservation of all the information, but we can still do fine. We're going to see in the examples coming up. So first question that you might want to ask is like, okay, so why not m greater than 2? Because we have shown that we could show 5 to 6D data before. So why don't we just encode? Why don't we just get a manifold of m equals 5 and then encode the third manifold as color, the fourth as shape, or something like that? Well, and that's the catch. That's the price we have to pay for the manifolds, for the manifold dimensions basically being so low, because the dimensions are abstract. So there's some combinations of the other attributes. They're just x and y. So if you would have x, y, z, a, and the other dimensions, they don't have meaning. So you don't know what to encode as what, basically. The conveyed structure is abstract. All that you're looking at is, do I have some clusters? Do I have the patterns in the data that I can visualize? That's all you can do. It just hopefully preserves stats and clusters faithfully. That's what you're trying to do with dimensionality reduction. It's a bit of an intuition to have. So, but you know, the x and y. What's important to remember here is that the x and y are coordinates are completely abstract. So you don't care that x is equal to 3.5 or x is equal to 5.6. The difference is meaningless for the observers. I mean, of course, there's math behind it. You can unpack why is it 3.6, but it's so unintuitive that that it has zero information to the reader. So you're just conveying structure, basically. And what we can still do, we can perform the following hybrid approach, basically. So we can select a small number of variables, which we could meaningfully encode as shape, color, etc. Then we basically run the dimensionality method, excluding the selected variables. So we're just going to select them, put them on the side. We're just going to run dimensionality reduction on the others. Then we display the manifold dimensions as x and y. We plot our scatter plot based on the manifolds we get from this step. And then we encode the selected variables as designed, basically. So an example of this, again, we have our iris data set, which is the data set of 3 classes of flowers, iris flowers. So what we have done here is we have those features, those measurements and parameters of these flowers are part of the data set. They're multidimensional. We're going to perform dimensionality reduction with the method called principal component analysis. We're going to go over that in a while. And we plot them using the x coordinate is principal component 1, principal component 2. So that's the abstract x, abstract y. And after we're done plotting it, we encode the class, which was not part of the dimensionality reduction features, and we are coloring it with the species of iris. So we can see that we indeed have 3 nice clusters that which are actually faithful to the data set. So indeed, versicolor and virginica are rather similar, but still separable-ish. I mean, not perfectly maybe, but with pretty good accuracy. And setosa is very different from the two. So we have, so for the iris data set, we have actually succeeded with our hybrid approach. Also note that M, the manifold dimensionality, can also be feasibly equal to 3, as long as we can interactively rotate. So on one of the previous slides, I have said that 3D scatter plot is fine. So M can also be 3. But however, let's focus on M equals 2 for the rest of the lecture for 3 cases. It's the most generally usable case. So you can you can be drawing this statically on a paper or on a slide. Those are two-dimensional anyway. And also 3D views are generally not very multi-view friendly. So if you would have 10 3D visualizations next to each other, I mean, 10 is an excessive number anyway, so let's say 5. And you're trying to correlate items, and you have to always move to a different sub-window, rotate the plot, and then go to another, rotate, and you're kind of spinning the plates on 5 views at the same time to connect and correlate. It's not that great, honestly. And in many cases, if you're reducing it to 3, then you might reduce it to 2 anyway. So I'm not sure how many % of the cases you have a small loss with m equals 3, but you incur a massive loss with m equals 2. So we're going to be general here. And if 3D views are suitable for your design, then note that all techniques that we discuss further can still be easily adapted to m equals 3. You just put that number in. Yeah. So do we have time? I think that's.
I think we have like 2 more minutes.
2 more minutes
now. So.
Yeah. So I think it's actually a good place to stop here. So are there any questions to the first part of the lecture?
Somebody is typing, so maybe if I find a person on.
We can wait a while. That's no problem.
Okay. Reitze asks, would fixing the different views with respect to each other when rotating improve its usefulness?
I don't think so, because if you're going to have multiple 3D views next to each other, then you're probably going to have different dimensionality reductions in each of them, right? And note how we have talked about the dimensions being abstract, right? So the x, y, and z in one plot are not equal to x, y, and z on the other. Now, if you would have if your multi-view is going to be, let's say, different subsets of the data, so they're going to be using the same dimensionality reduction, it's going to be like that you're going to do it once for the entire data set, and then you're going to show different parts of the data set in your somebody's unmuted. I hear quite some background noise from someone.
Sorry, that was.
No problem. If you're gonna show different parts of the data set with one dimensionality reduction, then you can indeed maybe rotate all if that's meaningful. It could be a nice thing to do. But in general, no. So if you're showing different subsets of the data set using the same dimensionality reduction, then it might have some value. That would be my full answer to the question.
Okay, the student says thanks. Martin is typing, so you may have a question.
Okay. But we can take a break, and we're going to start with answering Martin's question.
He just posted it.
Oh, okay, so okay. Let's wrap it up. No problem.
He asks, is there a sort of list that indicates which plotting technique, especially in a scatter plot, are better than others? For instance, plot over axis, plot over colors, plot in shapes.
Like you mean like a generic guideline for how to encode dimensions? Generally, I would say so. Basically, yeah, it's the kind of the perception primitives that we have gone over in lecture 2, right? So there we have seen that motion is the strongest pop out, but it's problematic, and then from the static pop outs, it's roughly color is greater than shape, and that is greater than the others. And you can use color and shape together to create separable dimensions. That's the gist of lecture 2, the kind of pre-attentive part. And basically, what you want to have is you want to. It depends on your purpose, right? So for instance, here, the key point to be conveyed is the categories of the irises. So it depends on your data set, right? So generally, it's very strong to encode color or color hue rather as categories. That's the strongest. Intensity maps to ordinal to interval plus variables, so interval or ratio variables, and but the correct answer depends on your data set, on what you want to visualize. So hence why the lectures have been theoretical. So they kind of give you the ordering of pop outs, and then it depends on your data set, basically.
Yep, he says clear. It's still Monday morning, so he'll take a look back at lecture 2.
Yeah. And I mean, keep in mind that we can always continue the discussion. So if you would have something like, okay, a plot. So do you think this is a good encoding or everything? We have instances of this in lecture 3 that I was critiquing or analyzing some of those plots. So we can always keep chatting in lecture 5 Discord channel, right, about this. But anyway, at this point, let's take a break. 5 minutes, so I'm gonna come back at 32, and we're gonna continue with the lecture. See you. Okay, so we have talked about the kind of overtures to dimensionality reduction. Now let's delve more into the actual methods. So there is a great survey from Laurens van der Maete from 2007, so which might sound quite dated, but it's actually quite still valid today. So might be a nice thing for optional reading. We're going to cover a couple of the techniques from the survey, the most famous ones that have been used and are still used, all of them throughout the world of information visualization. And I mean, principal component analysis dates to, I believe, 1901. So that's more than a century old, but still being used. And from the more modern techniques, we're going to take a brief look at TSNE and UMAP. And there's going to be some math, as I warned you, but I would like to emphasize that the aim is to understand those techniques on a very, very conceptual level. So know what they're doing from a global perspective. I'm trying to include the math because I don't like to mince my words. It's dimensionality reduction is all math, basically. And I mean, this is a master course, so I think that you deserve the complete or the complete useful information towards what's actually happening below. But we're still gonna only scratch the surface. So if you see some equations that look complex, don't worry. It's not that I'm gonna ask you in the exam, okay, write out the equation that does multidimensional scaling. Nothing of the sort. It's conceptual, intuitive level, and I'm gonna try to be as intuitive as possible. It's going to be difficult, but you can always ask your questions. Please do. But let's go in that. So first, let's start with the principal component analysis. Principal component analysis tries to find or tries to decompose your data into so-called principal components, and in each step, principal component is the unit vector pointing in the direction of biggest variance in the data. So which also kind of corresponds to the one that fits the data the best. So on this data set, we are trying to find an axis. So like we're going to try to rotate rotate lines from and find one which is going to capture the most variance. So where if that line, it's actually this line. So no need to kind of mark it as a spoiler. I mean, it's there on the slide. So if it's that one, this is the first principal component. Then we see that if this becomes the new axis, basically, so if we kind of rotate the data according to, so that this will become the new x-axis, that if we record values on this new axis, then there's going to be the most differences between all those sets, because it's going to fall on an interval that starts from here to all the way to here. And this is a nice animated example, like how might one find the principal component if we went iteratively, right? So these are the values that we're trying to record. So we're trying to find the axis where we have the most variance. Like if we go PCA2, that's actually, if this is actually a bad choice, because the interval only goes from here to here, or rather, actually, if it's oriented this way, then it goes from here to here. So the most variance is captured here. Again, it's fine if the biggest variance is a bit unintuitive. It's basically the one that fits the data the best. So we're fitting a trend line that becomes the new axis. So going further. So that principal component becomes your new x-axis, and you translate all the data values to it. So the translation means that you're just kind of recording the value on the axis as I have demonstrated visually. Then what you do is then you subtract the first principal component, basically the data captured by the first principal component from the original data, and you repeat the process. And this yields the second principal component, which becomes your y-axis for visualization purposes. So we're trying to find variance in the data and capture as much variance as possible within each successive principal component. That's all there is to it. Math-wise, so the one thing that I'd like you to remember, that's why it's bolded and even emphasized by color. You need to standardize your data before running PCA. So if you just take PCA as a black box, which is fine, you just have an implementation that you're going to run on your data. Do standardize your data before you run PCA, which means that you're going to transform it such that the mean for all your attributes, the mean is going to be 0, and the standard deviation is going to be 1. There are again library functions in most of the languages, including Python, I believe. Well, I believe there's definitely something in Python. I'm not sure in which toolkit, if it's maybe scikit-learn, but you don't have to do this manually, of course. And because if you don't do this, then the variables with the largest absolute values will dominate the principal components, even if they do not capture the most real variance, because this doesn't care about scale. So this cares about the absolute value. So if your variable 1 is going to be here, and your variable 2 is going to jump all the way here, then it has the higher absolute value. So then PCA will be considerably biased towards the second variable, which has higher absolute values. So this is a must. You have to standardize your data. Yes, we seem to have a question.
Yes, a question from Shores. Is a standardization that makes all values fall between 0 and 1 also sufficient for PCA?
That's normalization, and I think I mean, the recommendation is standardize. So the statisticians say, I'm not a statistician myself. The statisticians say standardize. So I'm a messenger here, you know. But you know, I would say normalization is better, definitely, than keeping it as is. But I mean, the statistician's recommendation is standardized, not mine. I'm just, you know, passing on the knowledge here. That would be my answer.
All right, thanks.
Yeah. So then, again, going over the PCA high-level algorithm overview, you're basically obtaining the eigenvalues and eigenvectors from the covariance matrix. So if these are senseless terms to you, then it's fine. But to those of you that might have done some deeper AI or data science, that this might add some intuition. We're not going to unpack all these terms because we don't have really the time in this lecture. But you know, if you know what these are, then this is what you're doing basically. Then you're choosing basically the m eigenvectors that correspond to the top m largest eigenvalues. So those are the kind of like native inherent vectors of your data. Maybe that's the way I can put it intuitively. Then you construct the projection matrix where its columns are the m eigenvectors, and you transform the original data set into the m dimensional space. So this is a slide. This is kind of like an extra slide for those of you that have worked with covariance matrices before, and that know algebra, or that have had algebra in your curriculum before. So, but for those of you, you don't have to really worry about this too much. If you're using PCA as a black box, then all of you have to remember this first point, definitely. But the others are for those that want a bit of an in-depth view. Another technique is multidimensional scaling called MDS. It's also a very old technique. I think it dates to the 1960s, but you would still see it sprinkled across InfoVis papers and visual analytics papers to this very day. And here, so again, very intuitively. So we're trying to map our n-dimensional data into 2D space, so that, or 3D space, so that we minimize the so-called stress. The stress is here, and basically, and the stress is nothing more than that we're just doing kind of least squares, the distance of the data in the original space. So the notation that we're going to have here is that x is the data in the original space, and y is the data in the reduced dimension in the manifold space, basically. So that's going to be across all the slides. So we're just subtracting the difference between we're just subtracting the distance in the manifold space from the distance in the original space. So just see how the distances differ in the original space and the new one, our reduced one, and we're pretty much just dividing it by the original distance. And the lower this number, and because we're using squares, we're using squares here, then we're doing a square root. But it's key basically that all this does is that we're trying to make the distances in the original space and in our reduced dimensionality space or our manifold space as similar as possible. So if 2 points have a high distance in the original space, we want them to have a high distance in the reduced dimensionality space, and vice versa. That's all this does basically. And this is just a formula for this. It's a very rudimentary formula, deterministic. It's not probabilistic, and it's based on the least squares method basically. So we're trying to preserve the distances. It's as simple as that. The next method is OMAP. So there it's very similar to MDS, but first we are going to construct what is called the neighborhood graph. So we're going to take our data points in our original space. We're gonna determine their nearest neighbors. So we're going to say, okay, so we can have one nearest neighbor, two nearest neighbors, and whatnot. And this will create a graph which is going to be connected by nodes, by edges, sorry. And instead of Euclidean distance that we have computed here, so this distance is Euclidean, we are going to compute the so-called geodesic distance, which is the sum of edge weights along the shortest path between the two nodes. So if we're, for example, going from, so this is a very simple example where each edge has the same weight. And we're going, if we want to go from xi to xm, then our geodesic distance is 3. So we're just gonna input these distances, and then we're gonna run MDS. So ISOMAP is a work from the year 2000, and it's there to kind of impose the neighborhood structure a bit more firmly into MDS, because MDS doesn't care about explicit neighborhoods, as you can see. It just cares about the distances between arbitrary data points. ISOMAP imposes a graph structure on top of our data, and then tries to minimize the stress, which means minimize the so basically minimizing stress in ISOMAP means that you're trying to keep the graph structure as preserved as possible in your lower dimensional space, in your manifold space. ISOMAP actually has two potential problems, and one is separate components. That's what we see here on the left. So if we select our neighborhood to be too small, then the graph will not cover the entire data set. So if we have a data set of 6 points here, and we select a too small neighborhood, then there will be no connections between these two parts, and effectively these distances are going to be infinite. The other problem is so-called short circuiting, which means that if we select the neighborhood to be too large, which you see here. Here we have the Swiss roll data set again. Then if the folds, basically, so manifold means that this is like the one manifold and it's folded into the roll. So that's what we mean by folds here. When the folds get too close, then the graph will jump to data instances that are not neighbors. So we see that neighbors are those data points along the sheet, along the rectangle that we roll into the data set. But if we select a too large neighborhood for our graph, then it will say, okay, so this is my neighbor. So for this point, we'll say this is my neighbor, and you will have false structure, which is very detrimental to the performance of the dimensionality reduction method. Further method is called stochastic neighbor embedding. That one is probabilistic. It has a horrible equation down there, but don't worry, we're gonna go over it very intuitively, hopefully. So all that SNE does is that the similarity between points in the original space, so points xy, xj in the original high dimensional space, the similarity is given by in a probabilistic manner. So it's a conditional probability that xi would pick xj as its neighbor. So you have your points sprinkled in your high dimensional space, and they have various distances from each other. So instead of assigning the distance or assigning the neighborhood like here, that we just say, okay, this is the nearest neighbor. So this guy is definitely my neighbor, basically, because I have assigned it by distances. Instead, you use conditional probability, and how this works. So all this does is that basically at each point, you will have a center of a Gaussian distribution, right? So that's the Bell distribution centered at that point. Except it's going to be ND distribution, not 2D if I draw it here. And all this equation does is that it sets the conditional probability. So this is the Gaussian for the distances between 2 points I and j, basically. So this is the distance. This is the distance Gaussified, and this is the sum of all the kind of Gaussians or all the probabilities by the other points that it will be their neighbor. Basically, the j will be their neighbor. So this is basically a normalization. So all we need to know here is that it's probabilistic. That instead of hard assigning your neighbor, we're going to assign it in a probabilistic manner using Gaussian or normal distribution. We don't have to remember this equation really. Then they do a trick that they establish the symmetric similarity, because the probability that I will choose j it might not be the same as the probability that j will select I mean, think of a real life example. So if somebody chooses someone as the best friend, it doesn't mean that the best friend might need necessarily to choose them as best friend as well, right? It's the same principle, and it's just normalized. So this is our final probability, the kind of symmetric probability that ij are neighbors. And these are some math consequences. So that's this is the symmetry that pji is equal to pij. The probability that I will choose I as its own neighbor is 0. That's hard assigned, and the sum of all similarities across all data instances is 1. So all these sum to 1 basically. This is important for the math, and basically what it does. So for MDS and isomap, we have talked about how they constrain the manifold, the reduced dimensionality space. So we're going to do the same for SNE. So in the reduced dimensionality space, to preserve the structure, it will also say that the distances are Gaussian, probabilistic, in the same manner as we have computed the p j conditional to I. So this is just like a final formula for the q's, which are the probabilities in the reduced space, the distances in the reduced space, and we're trying to preserve that structure, right? So this is how we're gonna get the distances in the reduced dimensionality space. And the final step, again, going on a very high level overview, we're going to minimize what is called the Kalbeck-Leibler divergence of P, which is the distribution of similarities in the original space, from Q. So that's the distribution of similarities in the reduced dimensionality space. So this takes the place of the stress function in MDS basically. So this is a formula that will give us how similar are these two probability distributions between the original space and the manifold space basically. And we want them to be as similar as possible, because so the divergence to be as low as possible, so that we see that our manifold space preserves the original structure as best as it can. And SNE is a nonlinear optimization problem, which is usually performed via gradient descent. So it takes some time to compute. So going over the method so far. So we have the PCA, which is about the variance. We have the MDS, which is about minimizing the stress from let's say hard assigned neighborhoods by Euclidean distance. Isomap does the same, but via geodesic distance, imposing a graph structure. And SNE is probabilistic basically. So our distances are probabilistic, that it's not hard assigned based on Euclidean distance. The problem with SNE actually is that this approach leads to considerable crowding problems, and this is part of the curse of dimensionality. So the problem with curse of dimensionality is that Euclidean distances in high dimensional spaces tend to be more and more similar to each other as we add dimensionalities to your data, or dimensions to our data rather. Sorry, not dimensionalities. What happens in SNE? So that's immediately a problem with the older methods, right? Because there we are hard assigning neighborhoods. So we are hard assigning neighborhoods, saying that xi is a neighbor of xj based on distances that become increasingly more similar. So that's problem A. But for SNE, because we have a Gaussian on top of each point, then we're going to cluster everything together because Gaussian distribution is short-tailed. So the data instances are going to be pulled towards clusters, and those clusters, and that's a problem of manipulation, might not really be present in the data in the first place. So we're actually manipulating the data considerably by using the vanilla SNE basically. So then we have TSNE to the rescue. That's one of the top methods still. And it's the same as SNE. So all the martyrium we just went through to explain SNE is still useful, but instead of using a Gaussian in the reduced dimensionality space, so we still use a Gaussian in the original data, but in the manifold space, in the reduced dimensionality space, we're using the student T distribution with 1 degree of freedom. Again, you don't need to really remember this. All whoever wants an intuition, how does this differ from a Gaussian? We have a sharper drop from the mean towards the tails, but we have longer tails than the Gaussian. So that kind of that extends our clusters. It really alleviates the problem of the data being clumped together in our manifold. Basically, this is the equation for this. We don't have to go over this in detail. Interested students can map this to the Qij equation on one of the previous slides. And then we again minimize the Kalbeck-Leibler divergence. So again, we want this reduced dimensionality space to be as faithful to the original dimensionality space as possible. That's all. And the final method I'd like to talk about is the uniform manifold approximation and projection, or UMAP, which is covered by myself here. And basically there we're going to go over super high level, so no more equations, I promise, because the math behind this is actually insane. But what it does, it constructs a neighborhood graph of the original data, so similar to ISOMAP, right? And then it projects it to the reduced dimensionality space. So that's actually similar to both ISOMAP and TSNE. But the graph is, again, a technical term, fuzzy simplicial complex. So what it means, UMAP again extends a radius outwards from each point. So similar like we have extended a Gaussian from each of those points in TSNE, we do the same with UMAP. And the radius is fuzzy. So the longer the distance between the neighbors, the lower the likelihood of connection. And when the two radii overlap from two different points, then the nodes are connected. That's how we construct the graph. So far, it's very similar to what we have done with SNE and TSNE. But the trick here is that the radii are chosen locally based on the distance to the k nearest neighbors. So a point that is far away from everything else will have a different radius than a point that is next to many points. So we have a local choice of radius. Wherever or in contrast to SNE, where we had the same kind of probability for each and every point. So that's the key difference. And additionally, we force that each point is connected at least to its nearest neighbor, so that we don't have the problem of infinite distances like we have seen in ISOMAP.
2 more minutes.
Okay, so this combats the curse of dimensionality. Which was, as we talked about, I have put this in text on the slide here for study purposes, that in high dimensional spaces, distances become the same-ish between arbitrary points in the absolute sense. So that combats this very nicely. And as I said, UMAP has quite some math behind it. I think the intuition is rather nice, but the math is insane. So the archive paper has 63 pages currently, so it's still being updated. So obviously we're not going over that. I mean, I haven't gone over that myself, to be honest. It's but it works actually really nicely. So we're going to start the next part of the session with examples. So now this the hard part is over. We're going to move more towards intuition. But from here, keep in mind that basically PCA is just capturing variance in your data. MDS is minimizing stress based on hard assigned distances, neighborhoods. ISOMAP does the same thing, but is about imposing a graph structure on top of your data explicitly. SNE does the same, but probabilistically, which alleviates the problem of Euclidean distances not working in high dimensions. And UMAP is one step further, so it's probabilistic, but also with local radii, so local choice of neighborhoods. So it's again a bit fuzzier, bit more adaptive. So as we progressed through the years, we have had more and more adaptive methods with more kind of accurate probabilities models and so forth. I think that's the progression that we want to take note of. But I mean, the details again, we're going to be talking on an intuitive level. Okay, are there any questions so far?
For now, I see no questions in the chat.
Okay. Fine. So if you have more questions later, if you digest these slides later at your own pace, then feel free to hit me up with questions. I'm gonna try to answer as best as I can, and like maybe shed some light, some intuition into some of those methods. Let's take a 5-minute break now, and I'm gonna come back at 10:03, I believe. Yeah. See you then. Okay, so let's continue with the lecture. Um, the knowledge in the previous section might appear a bit arcane to some of you at first, but again, we're going to continue with the intuition. So hard part is over. So let's consider one benchmark for to kind of illustrate the point of multidimensionality reduction. So I've already mentioned it briefly in the first lecture. It's called MNIST. It's a data set of 70,000 handwritten digits, 60,000 training images, and 10,000 test images. And the data is 28 times 28 pixels. So each of the digits occupies this visual space, which means that it's 784 dimensions in our data, and our individual values are grayscale. So I believe it's from 0 to 1 continuous, but I mean, I'm sure you could map it to 0 to 255. And the intuition here is, so we have 10 digits, right? The intuition is that if we do dimensionality reduction on this data, then we should pretty much have 10 clusters, right? We have 10 digits. Each of them or they should be very distinct from each other. That's what we have discussed in the intro lecture, that our Hindu and Arabic numeric system is visually distinct when it comes to the digits. So we should have 10 clusters, right? So let's see how our dimensionality reduction methods fare. If we use PCA, it's not that great, as we can see. So we seem to have one cluster here. This is also a cluster-ish, but this is a huge mess, right? So PCA might not be doing very well in our dimensionality reduction. MDS works like this. So this looks like art from Jackson Pollock. So that's again not a very good indication of clusters in our data. Maybe this one, but you know. Again, not so great result. If we do isomap, it's slightly better. So we can already see more clusters than we have seen before. So so the graph structure seems to help. If you do TSNE, then already we see quite some nice clusters. So TSNE has succeeded in our task. And UMAP is even better. So there we see clusters that are nicely separated. I mean, we see some artifacts like that. There are a couple of blue ones here, but overall this is probably the best separated out of all. Note that for some visualizations I have so this one is nicely illustrated with what the clusters actually are. I apologize for this one not containing any labels, but I found what I could find. So the main point is that we do have 10 clusters. So these are the 10 digits. We just don't really know what each of them is, but this has captured the dimensionality of the data very well. So UMAP, TSNE quite good. The previous ones leave something to be desired. So now let's move towards the design takeaway. So how do we choose the right method? So TSNE and UMAP come ahead as clear winners on the MNIST benchmark. And indeed, they generally perform very well on varied data too. So of course, we are not judging the dimensionality reduction techniques based on one benchmark. This is just a lecture shortcut. So I have shown this on a data set which has a clear expectation. But generally, if you read the papers, you will see better performance by TSNE and UMAP by far in modern works. This is just an illustration. And an important point to note is that notice how the MNIST visualizations all look completely different. So we have those clusters, somewhere, but none of these are very similar to each other. So not even those that succeed. The SNE looks like this, and UMAP looks like this. So yes, we have 10 clusters, but the data looks completely different. And this is exactly what I've been talking about in the first part of the lecture, that the x and y axes are completely abstract, meaningless to a human eye. So all we need to take a look at is the structure, not the actual the absolute positioning of the data on the axes. So they are really abstract representations, and this nicely illustrates that point. Going further with more examples of TSNE. So this is the co-authorship matrix of NIPS papers. So one of the most prestigious conferences in machine learning. We have a co-authorship matrix of papers, and we can see how similar different authors are from each other. And we see that the big names such as Geoff Hinton are indeed in the center. This is a nice TSNE projection of the Caltech 101 data set. So we see a big cluster of people here. We see some boat or sky scenes, because there's a lot of blue in those images. So we see that those clusters are meaningless. Boats are actually here. Sorry. So we have prominent sails, and yeah. So that's another example of how TSNE works. If you would like to compare TSNE to UMAP, so this data set is called the fashion MNIST. So it's again 28 times 28 images of 10 classes, but each of those classes, instead of being digits, are pieces of clothing. So t-shirt, shirt, pullover, coat, dress, sandal, sneaker, and so forth. And we see how the clustering how the dimensionality reduction works for data that is slightly different from the digits side by side. And an example of UMAP, a nice one, is a data set of butterflies being UMAPed, and it's instead of it floating in the 2D space freely, it's been snapped to a grid basically. So here we see progress from butterflies that have translucent wings all the way to dark winged butterflies basically. So it's a nice again illustration. So to choose the right one. So regarding the state of the art, UMAP is the top performer nowadays in many applications, and it's growing further each day. TSNE is the standard of the past decade, basically. So you still see it a lot today. So I don't think that if you would write a paper and include TSNE as your dimensionality reduction method, that it would be rejected. But UMAP is overtaking TSNE lately, and these two are the generally recommended choices. So if you in your practical work or in your further career, if you need dimensionality reduction, you really cannot go wrong with UMAP and TSNE. Implementation is available for major languages, including Python. I have included the links, so you can download it there. And know that UMAP is also faster than TSNE, because a lot of that crazy math that I have hinted at is aimed at the entire thing being way more easily computable. So there is a lot of high level math intuition to simplify things. And TSNE is slower, because, as we discussed, minimizing the Kalbeck-Leibler divergence is a nonlinear optimization method. So it's not very simple. There have been great efforts to make TSNE faster, and the efforts still continue. So TSNE is much faster than it used to be a couple of years ago, but UMAP seems to be the faster choice, considerably so. So UMAP or TSNE those two are your default choices, your black box choices, basically. I would also like to make a case for PCA, if you have the niche usability for it. It's very fast, because the modern implementations do not have to compute the covariance matrix, which used to be the performance bottleneck. And PCA is the most interpretable out of all, because the principal components are actually, if you look deeper into it, are actually linear combinations of attributes. So if you can read that, if you can read matrix notation, if you can kind of write the linear combinations in a polynomial, you can kind of unpack what the individual axes are. And I think this is actually quite nice, because it will nicely illustrate the correlation in your data. So if you have a principal component where it's like a lot of attributes combined and they are kind of the same-ish, then it will really unpack the correlation between attributes in your data. If you can read matrix notation, or if you are willing to take the extra optional step for this course, but might be good for you if you're interested to kind of go over how PCA really works. Then you can then interpret your axes. You cannot do that absolutely with MDS and the MDS plus, basically. So MDS and the other techniques are all pretty much nonlinear. So you will not have any luck interpreting them. So that's why PCA might be nice, but note that this is still not very accessible to your viewers. So if you show an axis and you say, okay, but this is a linear combination of attributes 11, 22, and 35, people will not really digest this information, or your viewers in the general case. So it's more for you, basically. But there is a case to be made for PCA, but as we have seen on the MNIST data set, it's massively outperformed by the TSNE and especially UMAP. And to kind of conclude the dimensionality reduction portion of this lecture, so the dimensionality reduction techniques are definitely useful and powerful. Remember, you are always losing information from going from ND to 2D, even with the best method there is. So even if you use UMAP, you are still going to lose information. You have to remember that. And I mean, of course, unless the actual manifold dimensionality is 2D natively, and your best method can perfectly capture the manifold. So basically, it can unroll the Swiss roll perfectly, kind of. But that case would be very, very rare. So this is true in over 99% of real cases. And you have to think very hard of the effect of this information loss on the conclusions drawn from your visualizations. So we have talked about Anscombe's quartet. You cannot just summarize the data. You also cannot just dimensionality perform dimensionality reduction to your data and then call it a day. So that's why we have multi-view visualizations. That's why we have interaction. Why we have interaction such as abstract elaborate. So it's a powerful technique, but just performing dim reduction on a data set is not enough to visualize it reliably. So it's one of the tools, but not the tool, basically. Right. So this was the big chunk about the dimensionality reduction, and now we're moving in the survey towards the visual mapping techniques, and we're going to talk about visualizations finally. So what are the visualizations to map multivariate data? The first and very well-known one is the parallel coordinate plot. Again, our beloved IRIS data set. On the x-axis you have your individual attributes. So these are the attributes: petal length, petal width, sepal length, sepal width, and on your y-axis are the actual values. And the lines are individual data instances, and which can of course and should be color coded to encode categorical or ordinal variables. So here we have our three classes: Setosa, Versicolor, and Virginica. So we have talked about Setosa being a bit more different than the two, but the two being still being separable. And this we can see especially in this part of the plot, right? That we have them nicely stacked, nicely ordered, and this is where it gets a bit messy. So we have to be careful about ordering of attributes. We've actually touched on this in lecture 3, I believe. Sometimes you will see a lot of clutter if you just order the axes differently. So you are allowed to select those that show class separation, so or order them such that they will show class separation. And it's good to start with exactly those. So here it's a successful plot because we don't start with this, because the natural reading order is from left to right, right? So we're going to start here and say, oh, nice, this is separated. I see the three classes now, and this is okay. It's not as simple. It gets messy here, but it conveys the point that we want to make. you can separate them on these two attributes on petals, and the sepals are, you know, not so great. So this is a successful plot because they have selected their attribute ordering correctly, in my opinion. So what are the pros? So the nice thing about the parallel coordinate plot is that it enables visual classification, right? So exactly what I have shown on the previous slide, what we can do with the separations, that's visual classification right there, and it immediately pops at us from the plot if we look at it for at least a couple of seconds. So it can be analytically very powerful. So it can be analytic visualization if you can reorder the coordinates interactively, especially. So if you, for example, would display this as the big mass, but you would allow the, let's say, the reconfigure that's an example of the reconfigure interaction, that I would be able to put this here maybe, or this here. Then it can be a nice analytic tool, so that the user can, if you don't know what your classes in your data are, then you can give this kind of powerful tool to your users to be able to select themselves. The main con is that parallel coordinate plots are very prone to clutter. So you cannot show too many data instances. You will need some filtering and selecting, and sometimes it can lead to false conclusions due to the ordering. So you know, it's a bit of a double-edged sword. And also, it only really works for data with 5 to 10 dimensions. So this is a parallel coordinate plot for 28 or something abstract attributes, and we don't. So we have clutter here. So it's also cluttered, but here it's a bit difficult to follow. It's too much on these axes. So you know, really, if you have 5 to 10 dimensions, that's your best bet. Very low tens would be so, but for 30, it's not so good. An extension of parallel plots to categorical data are parallel sets. So this is our data table for some kind of abstract demographic data. So we have categorizing by sex and by color, which is whatever. It can be some phenomenon where you respond with three different answers. And you can visualize it like this. So you can have a connection between. So here we have male or female, and here we have red, green, or blue, and here you can kind of see how these how the populations flow from each of those each from those answers that were asked in that survey, or the possibilities that were asked in that survey. Another dimension that we another plot that we have, I'm still in the previous part of the lecture, maybe mentally. Another plot that we might want to use is what is called a star plot or radar chart. So there are two pretty equivalent terms. So pick your poison. And again, if we visualize our favorite iris data set, then a star plot of it looks like this. So our axes are arranged in a circle, as you can see, and then we are visualizing here. It's possibly the averages. We are visualizing them on the individual axes, and we're also coloring the area between those 4 points, basically. And again, we can see that it successfully conveys the message that Setosa is completely different, and versicolor and virginica are quite similar but still separable. And here, an additional piece of information that overall virginica seems to be larger. That basically the separation is on the overall size. That virginica seems to be a larger flower than versicolor, but the angles are very similar. So it seems that the structure of the flower is kind of same-ish, but it's just scaled up. So that's some nice additional information that we see in a star plot. And I mean, to an extent, we see it also in a parallel plot because there's also, you can compare the values, right? But here it jumps out at us a bit better. So the pros and cons are very similar to parallel coordinates. This is yet another example of a star plot, just with five different axes. So again, we have to be careful about clutter. The ordering of the axes can be very important, and yeah, it's again this similar conclusion. This is a bit of a different variant, and one advantage of star plot is that you can use it also in this way. So to combat clutter, if you have let's say low tens of your data instances, you can plot the star plots separate to each other, give a legend, and then people can compare between individual glyphs. Here we see an example of NBA players and their game stats. So this is something that you cannot really easily do with a parallel plot, because those individual plots don't work as well as glyphs here. So this is a nice technique to alleviate clutter. And another plot which is very popular, this is probably statistically the most sound of them all, is the scatter plot matrix. So if you have n-dimensional data, you have an n times n matrix of scatter plots, and basically this is a kind of mathy way to write that you're going to be plotting on x-axis the first, second, third, fourth, and fifth coordinates. So MPG, DISP, HP, DRAT, and WT. And here the same. So WT, DRAT, HP, DISP, MPG, basically. So each of these scatterplot matrices is this. On the x-axis, basically the first attribute against the first attribute. This is going to have the first attribute on the x-axis against the second attribute, and so forth, basically. So you always have like a pairwise plotting of attributes. So this is brilliant to see correlations in the data, of course, and which is the point I write on this slide, and it's also very comprehensive. So it shows all the data. So you will see the data in a multidimensional setting in its true form. So it's a very useful thing, and you can kind of individually inspect relationships between individual attributes. Of course, the weakness is that you cannot inspect the relationships between 3 or more attributes at the same time. That's a con, but it's
2 more minutes, by the way.
Okay. But this is statistically probably the most sound plot. The con, well, it can be overwhelming because you're showing a lot of information. And again, it's only useful for max 10 dimensions, because 10 dimensions is already 100 scatter plots. So 10 might even be quite excessive, right? So again, the dimensionality cannot go too high. Note that we have seen this before. So for scatterable matrices, it's very, very good if you add the connect interaction. So you allow the users to select data points they're interested in, and you will show the same data in your other matrices. It's a great help with the feeling of being overwhelmed. Of course, scatter plots are not very useful for categorical data, because then you will have graphs like this, which don't really convey much information. So you can add variable specific visualizations instead of the scatter plots. So you only use scatter plots where they make sense, and elsewhere you use bar charts or heat maps, whatever you prefer. And this is just an example about late aircraft delay, and illustrating the generalized point. So let's stop this part of the lecture here. Are there any questions right now?
For the moment, I don't see any questions in the chat.
Very good. So let's reconvene at.
Actually, there's a question now.
Okay.
Just popped up. For the star plot radar chart, why are the straight lines between attributes rather? Oh, why are there straight lines between attributes rather than curves?
So the question is, so why is this a line rather than a curve? Well, I actually don't know, honestly. Yeah, so this is something that we would have to kind of deduce ourselves. I can look it up, but I don't know the answer to this. This is kind of the traditional way to draw this. But note that actually there is a variant. So some people draw it as these kind of like these weird kind of Frankenstein pies. So you know, so there seems to be both ways there. So but the traditional plot is definitely this, where you draw the straight line between the individual points. I think because it's the simplest. If you have 2 points, then you just connect it with the line. Here it's used with the wedges. So both are valid, but I don't have a let's say an impromptu opinion on which one is better. This seems to be better at if you have it separately like glyphs. So if you're comparing the players between each other, here I think the straight line case could be made for the straight line conveying the point about the size better. I think if it would be a curve, or if it would be like a semicircle or whatever, then well, it's going to be a curve, it's going to be an arc, right? Then it might not pop out that well, but it also could. But you know, again, this is a very very impromptu answer. I don't know the scientific answer to that, but both seem to be used in my examples.
Now some more questions came up. Tom asks, for the star plot, isn't it better to only draw the outlines instead of filling them, since that can change the color when they overlap?
Yes, absolutely. So these examples. So a star plot is also valid if you completely forego the filling, but the filling can help you with the Gestalt law of closure, right? So if you so it will kind of, because you have lots of those curves, and you could have, so if you would have, imagine this plot, if it would be so for like the, let's say the example, let's imagine it that it will not be filled, and it will also be the same color, right? So that would be quite difficult. So the colors might help, but again, if you want to compare glyphs, so if you want to compare more radar plots, then this I would say works better if it's filled out. And here I would say that if you have a low number of data instances, then it would even might be better to draw a line without filling it in. But if you would have 10 gymnasts here, I would say then it would be, well, it would be cluttered anyway, even with the shading. But even though you have these kind of overlaps, color overlaps, so they don't mean anything, you are still kind of able, from this shading, from basically from the points in your plot where it's only one of those instances, you can kind of piece together the entire thing a bit better. So I wouldn't say it's wrong to draw it without the shading, but I could see the reason why they're using it here.
Yeah, sorry. Then, like Thijs asks, is a radar chart basically just a parallel coordinate plot, but radial?
That's exactly what it is. Yes.
Yeah.
Yes.
Yeah, Ahmed is still typing a question. I'm not sure how fast he's typing, but
Okay, let's wait a while. The question is going to be answered anyway, so for sure. But let's wait a bit. Okay, do we have it there already, or?
I feel like it's more like another answer to a question. So
Okay.
not really a question.
So I'm going to review this, of course, afterwards. And if questions pop up during the break, then we're going to start with answering those. But let's take a break now for 5 minutes. So I'm going to come back at 37. Then see you. Okay, so let's continue with the multivariate visualizations. Another one is called the trellis plot. So the trellis plot, the idea is that for each subplot, the x and y axis is the same. It will always plot the same two variables, and each plot will correspond to a certain configuration of categorical and low dimensional ordinal values of other attributes. So here, for example, in this instance, we have the yield of various strains of barley in towns of United States in 2 years. So here we always say that each of these plots is essentially it's actually essentially a bar chart, right? Except it's done with this minimalistic way where you, instead of a bar you just have a point. So it's kind of like this bar-ish scatter plot. And here are the strains of barley. Here is the yield, and for each of these plots in this row is the year 1932 in various towns of the US, and this is the same for different years. So you can compare the yield between towns for a certain year like this, and you can compare yields for the same town in different years like this. So this is and the reason it's called trellis plot is that it looks like this trellis where you're growing let's say, I don't know, grapes on these kind of wooden stakes. So it looks like that, hence the name trellis plot. And this is a basis and flagship visualization for Tableau, which is a famous visual analytics tool. We're going to see an example tomorrow. The pros of trellis plots is that they allow to see relationships between the so-called switch variables. So the switch variables are the towns and the years, and the individual plots are completely flexible. So you can use whatever works best. So here we're using these plots, but you can add bar charts, line graphs, whatever you desire. And the cons is, well, you guessed it, it only works for low number of categorical ordinal attributes. So if you would want to visualize it for the last century, then it would be quite a plot indeed. So regarding the multivariate plots, the design takeaways, there are plenty of techniques. Parallel coordinates plot, star plot, or radar chart are nice for overview or for non-analytic viewers, and scatter matrices, trellis plots are more about the stats and relationship of values. But of course, we have seen a common weakness. So none really works past more than 10 dimensions, because at least in the static sense. So if you want to kind of cram everything on the screen right away. So, but if you introduce interaction to allow attribute selection, so people can select their dimensions that they want to visualize, that will help tremendously. So that's definitely a consideration for possibly your projects. And the final chapter I would like to discuss is our glyphs, basically. So glyphs, we know what they are. So they should be they represent individual data points. They should be simple and discernible, right? So but what if we had a manageable number of data instances and multivariate data, right? So that we could kind of maybe encode more detailed glyphs somehow. And there indeed have been works on more elaborate glyphs that convey multivariate information. And these glyphs are alternatively known as icons, and they encode high dimensionality by using shape, color, opacity, size, location, basically everything that goes against the pre-attentive laws, as we have said. But still, they try to kind of pay this price and make the glyph design as intuitive as possible to offset this. And they need to be small, and there need to be multiples shown at the same time, so that you can compare them between each other, and that you can kind of visually sort them, right? We have already seen an example of this. So this is so these star plots are what counts as glyphs too. So each of those players are individual glyphs, and we can try and compare them between each other to gain insight into the performance of the NBA players. The most famous example of this probably are the so-called Chernoff faces. So Chernal faces encode high dimensional attributes as rudimentary facial features, as we see on the in the example below. So if we have the crime statistics in the United States, then we have encode height of face, height of mouth, shape of face, width of eyes, height of eyes, and width of mouth. And these basically, so the aim here is that we kind of invoke the facial recognition software in our brain to enable comparison. I mean, I have mentioned this example in lecture 2, that we have special neurons for recognizing faces. So this tries to leverage this. Neat idea, right? So this is the example. So this is how the crime in the US looks. So we see quite a weirdo here of the District of Columbia. This is the average for the United States, and you can kind of compare the different faces. So those are the Chernow faces. That's the glyph example. It's a nice idea, but are they really useful? So have we been able to glean something else than District of Columbia is completely different than everything else here? There's divided opinion on this. So each InfoVis course over the world teaches Chernow faces. So does ours. But I would say that modern InfoVis opinion and mine as well leans to that they are not actually that useful. It's a nice kind of idea, nice to demonstrate glyphs, but the problem is that not all facial features are perceived equally, right? So if you consider, for instance, eye size versus curvature of the mouth. So if you swap these, you would draw entirely different faces if you like swap attributes encoded into these, and this would lead to completely different analytic conclusions, which would distort the data. So you want your viewer to draw conclusions that are correct to the data that you're presenting. And the problem is that, of course, you can swap freely because you alone choose what you encode as each of that dimension. So if we do this little kind of trial by combat or baptism of fire, or however we would like to call it, I cannot think of any notorious and successful multivariate visualization hinging on Chernow faces. So this is a nice example of a I hesitate to call it a failure case, right? But the idea seems really nice that you kind of invoke this facial recognition software, and that could be quite an interesting thing, but it kind of fizzles. So glyphs are very difficult. That's the takeaway from this part. And if you actually look at this systematically, there are a lot of things to consider when designing glyphs. So it can be done, but we have to be very careful. So the desirable characteristics of glyphs we have mentioned mentioned two already, that we want to compare and we want to sort, right? Visually, that if we see the glyphs next to each other, we would like to sort, and especially sorting is very difficult if you do visual sorting. So I mean, you can try this yourself on the NBA players. So pick a stat and try to sort them quickly according to the certain stat that you have picked. There has been systematic work on how to design these glyphs properly. Again, optional reading for our course. Some of these desirable characteristics are typedness, so the appropriateness of encoding of each attribute with respect to the attribute variable type, visual orderability. So can we sort this easily, which is problematic usually. Channel capacity, the number of values that can be encoded well within a dimension. Then it's separability. So when two or more attributes are encoded within the same channel, so you're kind of having mini glyph within a bigger glyph, then you should minimize visual interference. Then it's searchability, so that you can quickly search for individual values. So if you're interested in a particular attribute, you can quickly search for it within your glyph. Then it's learnability. So if you look at the glyph, you kind of easily grasp how the glyph is constructed, and it should be easy to remember as well, so that you don't have to keep looking at the reference to see the definition again. Then we have attention balance. So levels of attention should correspond to the level of importance of the attribute. You should be most prominently encoding the attributes that are the most important if you have an importance ordering of your data. And then it's focus and context. So we should go for an easy identification of individual visual channels under a specific interaction. So like if I hover over this column. It's better if I have it highlighted in color than if I only have intensity highlight. So just a brief example to give you. This is so what has been considered a nice work is that you can visualize rugby matches. So here we see how we can visualize various dimensions. So this is just an example. This is maybe to look at it later. We're not really gonna unpack it with respect to these seven attributes, or eight. Are there eight rather? But just you can encode various information about the rugby matches. Here it is. Here it is nicely decomposed. How you can because I'm not a rugby person, so I don't really understand this. But this is being given as one of the successful applications. Then we go on with encoding of these variables.
Thijs asks,
Absolutely.
Oh, for after, yeah, I just asked it now. Why are Chernoff phases so influential? To be honest, it seems like a terrible and stupid idea.
Well, yeah, it's but the thing is that if you look at so you see that I mean, your opinion is very strong. I put it very diplomatically here that the modern InfoVis opinion leans to no. It's because this idea about those glyphs is very tempting to the InfoVis community. So I mean, this course, of course, is not supposed to be like just an opinion piece of mine, right? But it should cover the kind of most kind of influential works in the community, even if I agree or disagree with them, right? So you should know about these glyphs, and lots of, so you see that there are some references here in the survey that people keep working on this, and from the rugby glyph example that I've been talking about, that is there, that one is considered useful for sports analytics. So there is a way, but lots of them are terrible failures. That's actually including the most famous case of the Chernoff phase. So that is. It's kind of, let's say, a warning case from trying to be too fancy, right? So lots of visualization designers, it's a bit of a meta point to be made. Lots of people that design visualizations try to be really fancy, but that's not what a visualization is about, right? You're making your data or your question more accessible. So you wouldn't believe that lots of people still try to do these Chernoff phases. They're even part of statistical packages for various programming languages, and even like for statistical languages themselves. So if you, for example, are familiar with the R language, there's a Chernoff package for that, which is part of the standard distribution. I have no clue why, because this is not that useful, but it's a thing. It's a thing to know about InfoVis, and that glyph design, even if it looks like could look nice at a first glance, like a nice idea, it's just a gimmick, but people still are attracted to these glyphs. So I'm trying to say that it's you have to be very careful with what you're trying to visualize with glyphs, and only a select few have been successful. That's the entire point of this section, I guess. So yes, Chernoff faces are a bad idea. Yes.
All right, yeah, maybe we can ask the rest at the end.
Okay, we're approaching the end very fast already. So these glyphs. So this has been used for rugby analytics. So this is a glyph that encodes 1, 2, 3, 4, 5, 6, 7, 8, 9 dimensions. If I see it correctly, this is the blueprint for encoding it, and they have used this kind of plot as the analytics. But again, I'm not a rugby person, so I cannot testify the usefulness of this method. Maybe if we have some rugby fans in the audience, maybe they can chip in with their opinions. But this has been mentioned as one of the few cases where glyphs have actually been successful in encoding visual information, and that's indeed the kind of the point that I spoiled a bit. That they can be useful if you know what you're doing. But you really have to be careful that they are not just a gimmick, much like, in my opinion, and many other people's Chernoff faces are, and that they are actually usable. and losing the pre-attentive benefits is a very steep price to pay. So my design recommendation for you would be to avoid trying designing glyphs. They're not gonna give you the greatest mileage, and I mean, unless you really know what you're doing, just don't. That's the advice. But indeed, it's a subdiscipline of InfoVis, and people are doing this. So for the sake of objectiveness, there seems to be some value in it. But it's, I think that breaking the pre-attentive laws is not very good. Yeah. To conclude our lecture, multivariate data is always a challenge. It's very tricky to rely solely on statistical summaries. So recall the Anscombe's quartet. Dimensionality reduction techniques are useful, especially for high tens or more attributes. So because they can do it, they are powerful enough to reduce high dimensional data as accurately as possible. But note that there is information loss in the transformation to be seriously considered. Then we have multivariate plots that can convey analytic information and even correlations, but they are prone to clutter and unusable. Well, unusable with more than 10 dimensions. I kind of forgot to write that there, so not unusable, period. But I'm gonna correct this. Interaction helps with both. So especially when the user can filter attributes, reconfigure, if they can show detail for your dimensionality reduced data set, interaction is really a key ingredient in tackling multivariate data. So adhere to the interaction theory that we have shown in the last lecture. And regarding glyphs, there is potential, but they definitely lean towards being a gimmick. So here are already the references. So that's all for my lecture, and let's take care of any questions that might have arisen.
Yes, so there's one from a bit earlier, from slide 62, from Sanne. And she asks, why, or maybe I'll first, okay, no. Why are scatter plot matrices normally shown in a square? Couldn't you better only show half of the data, less overwhelming? As now we see more or less the same correlation plot twice, MPG versus disparity, I don't know, and this versus MPG.
You're absolutely right, and that's what we have here, right? So people definitely do this. Yes. So one thing that why I believe somebody could make a case for basically repeating the same information in the top half. So that's a very accurate observation. Is if you do something like a row wise reading, right? So if you say, okay, so I am fixing the column, and I'm trying to see, okay, how does it correlate with the rows? Then it's good if you have the complete information here. So even if it's kind of repeated across the diagonal. Same here, right? So you can say, okay, so on my x-axis I have the HP, and I am trying to see kind of the how it is with the columns. So that kind of allows you to do maybe some kind of correlation, or like glean some details about relations between three or more attributes like this visually. But I agree, this information is equivalent to this information, and you can absolutely show the bottom part of the scatterplot matrix if that's sufficient for your case. Yes.
All right, thanks. This we already asked. Then Roland asked, does appropriateness mean the level of how it's related it is to the date? I don't really know the context.
I don't either, I'm afraid. So Roland, could you
see with us,
write more details about your question? So I'm not sure what this refers to, I'm afraid.
Roland is typing.
Hello, yes.
Yeah, you can ask. Yeah, absolutely. You can ask in voice. Hi.
I was unmuted. Yeah, could you re-explain just the appropriateness again with those in relation to the use of glyphs with the comparison, how you can sort it, and typeness. And the typeness side, yeah, typeness.
Yes. Yes. This word. I see. Yeah. So how I believe this is that basically you should how I read this is that you should encode variables as like meaningfully, basically. So for instance, you should not encode color hues to interval data, right? Because the hues are not ordered on a continuous scale, right? So if you have categories, you should encode them as, so basically properly encoding your variables based on their type to the visual primitives in your glyph. So basically using the design suggestions from lectures 2 or 3 correctly. That's how I read this rule, if that makes sense.
Okay, thank you. Yeah.
No problem. Do we have any other questions?
Yeah, I think there was some more. Yeah, this is more than about the exam. That's the last question. And I might ask, what is the exam date and what type of exam will be made?
Yes. So as I said before, so the date for the exam, I believe, so check in data notes. I think it's on the 22nd of March. So that's like 1 week after the course ends. So that's rather soon. But I mean, I have no power over the scheduling. That's done centrally by the university. And regarding the type of the exam, so there are multiple concerns to be made. I have written a couple of answers about this in the Discord already, but maybe it's useful to summarize this also in voice. I would like so I am going to release a trial exam soon-ish. I would say I would aim to have it in the maybe sometime in the next week already. Failing that, the week after that. That will kind of give a demo. The thing is that I'm completely new to online exams, especially and InfoVis has an additional problem that it's not 100% objective discipline, but I have to give you an objective grade. So I'm still grappling with this to make it as objective as possible, but still getting some insight into how you have mastered the material. So I do aim for this for the exam to be design oriented. So you will be basically given I think that the main component is going to be that you're going to be designing a visualization on paper, of course, not in code or programming anything. So it's going to be or in paper / any appropriate medium in the exam tools, which I'm going to familiarize myself with soonish. So that's what I mean by on paper. Okay. And yeah, and I'll have to make it so that you can demonstrate your knowledge of the material, and with me being able to grade 200 exams within a reasonable time. So all of these concerns, I'm still working them out, and I'm trying to have an answer ASAP. But just so you know what my situation is with this. So yeah, that's the answer, I guess.
Do you plan to be a proctored exam or unproctored exam?
I'm not sure about that either. So personally, I don't believe that like in the online sense, it's difficult to make a truly kind of proctored exam, right? It's that's why I want to focus on the design. So the design is that even if you can read the slides and everything, and you haven't learned them, you won't be able to finish on time, right? So that's why I want the design, but I cannot say if it's going to be proctored or non-proctored, because I also might want to include a couple of questions that could be let's say a simpler choice or not so elaborate in those answers, and for that we might need some form of proctoring. Yeah. So I'm gonna all I'm saying, I'm gonna try to do this ASAP. I've been working on this since the course started pretty much, and but I still don't have the definite answer, and I don't want to make any promises right now because I'm not at the final form of my exam yet. Yeah.
Yeah, I think there are no other questions anymore, or I don't see any more.
Okay, so thank you all for coming to the 5th lecture. I'm going to see you tomorrow, and have a nice day. See you.